In this small example, we got just 5 nodes. So 5 nodes labeled as 1 to up to 5, and there are altogether 10 possible sessions. Okay, let's say a session between 1 and 2, 1 and 3, 1 and 4, 1 and 5, then session between 2 and 3 going through this path, right? 2 and 4 and 2 and 5, and so on. There are altogether 10 possible sessions among these 5 nodes, and there are 5 links, bidirectional links. We can look at the degree distribution here. The degree distribution for this graph is very simple. It's 3, 2, 2, 2, 1. Okay, of course, this is an extremely small example to illustrate our point, but this enables us to write the matrices and optimization on a single slide. All right, so let's look at, call this graph G1. Okay, let's look at S of G1 and P of G1. The small s of G1 is easy to compute because the sum of the didj's for all the ij's that are connected. For example, nodes 1, 2 are connected, so the first term is D1 plus D2. And there are altogether 5 terms here. D1 plus D3 plus D1 plus D5 plus D2 plus times D4 plus D3 plus D4. Okay, it's all associated with the left graph. We'll talk about the right graph in a minute. So you can add this up. For example, the first term is 3 times 2, okay, with all the terms, and then you get a number 23. Okay. Now, how do we find the big S of G1? We need to know what kind of graph with a node degree distribution of 3, 2, 2, 2, 2, 1 would give you the largest small s. Well, if you look at all these terms, you see that the best way to do that is to make a simple swap. Okay, instead of 3 connect to 4 and 1 connect to 5, 1 should connect to 4, because then we get a term of 3 multiply 2 instead of 3 multiply 1. Okay, so switch 1 to 5 to 1 to 4, and then switch 3 to 4 to 3 to 5. You can verify that in this right-hand graph G2 called, it has the exact same node degree distribution, 3, 2, 2, 2, 1. Again, it's not exactly Pareto, but it suffices to illustrate our point of trade-off between S of G and P of G. Okay. And then you can carry out the computation for small s of G2 is 24. And therefore, big S of G1 is small s divided by the maximum s you can get out of all the graphs with this degree distribution, which is 24. So it's 23 out of 24. And clearly, big S of G2 is 24 out of 24 is 1. So 1 is less than 1, the other is 1. Therefore, this graph, G1, is less likely to be drawn at random than G2. Just like internet is less likely to be drawn than preferential attachment type of topology. So now the question is, what about performance? P of G1 and P of G2. Let's run this exercise for P of G1. P of G2 is very similar. Okay. So we just calculated the likelihood already. Now here's the performance. So first of all, we have to write down this routing matrix R, which is 5 by 10 because there are 10 possible sessions. Okay, and the variables is basically x1, x2, down to x10. And there are 5 links, 5 nodes here. Okay, so R is 5 by 10. Let's say the first session is the session of session 1. It's the session that goes from node 1 to node 2. And therefore, is simply 1, 1, 0, 0, 0 is this column. Because the first session goes through nodes 1 and 2 and no other nodes. Okay. And the second session, which is, let's say 1 goes to 3, again, it's very simple. It's just 1, 0, 1, 0, 0 now. And you can fill out the rest of this routing matrix. Okay. Next session is 1, 1, 0, 1, 0. It's 1 to 4. And then it will be 1 to 5, which is 1, 0, 0, 0, 1, because 1 is directly connected to 5. And then it's the session 2 to 3 now. Okay. We'll see that in order for 2 to go to 3, you'll pass through node 1. So this session, the fifth column, is the session number 5, going from node 2 to node 3. And the path will traverse the following 3 nodes, 1, 1, the first 3 nodes, 1, 2, 3. So the entries in this column is 1, 1, 1, 0, 0. So you can fill out the rest. And now, with this routing matrix constructed, we say this matrix multiply our variable should be less than the total bandwidth available per router and out of these 5 nodes. Let's say the BKs are exactly the same as the degree. They don't have to be, just to make the numbers simpler. And therefore, they are 3, 2, 2, 2, 1, basically. So the total bandwidth number of packets can process is directly proportional to their node degrees. So per degree, basically assuming has a unit capacity of processing. So subject to this constraint, okay, and the definition that each x is really rho times the demand and the supply. So we can make up some data for these y values. Okay, for example, we're going to say the y vector is 5, 2, 4, 4, 2. And therefore, for each session, there are 10 of them. You can look at what are the source and destination, multiply the number, and then you get another constraint. So constraint 1, constraint 2, subject to these 2 constraints, maximize the summation of xi. That's the objective function for performance. Now, if you solve this very simple linear optimization problem, you get the following answer. The following answer, x star is some vector, actually doesn't matter. Rho star actually doesn't matter. It turns out to be 0.033. But that's not the key. The key is that maximize the sum of these end-to-end sessions throughput. That is, the performance for this graph G1 is 3.73 certain unit, let's say gigabits per second. Now we can carry out the exact same procedure for this graph G2. Okay? And then you're going to get a different number. It turns out that the performance for G2 graph is 3.03 gigabit per second, which is clearly smaller than 3.73 significantly. And the reason is quite clear, because in order to make the most highly connected node to be sort of in the center of this very small graph, you're actually creating a performance bottleneck in supporting throughput. So now if I plot the location of G1, G2 in the P performance versus S likelihood, normalized likelihood graph, I see that they follow the same trend as the internet versus preferential attachment. Except this is a much, much smaller example. So we get a very small dynamic range, but nonetheless, you see the qualitative trade-off between performance and likelihood. So that is our small example, and we are going to conclude this part of the lecture. In the advanced material, we'll say a lot more about both preferential attachment and constraint optimization as generative models of scale-free networks. And And there's a very rich and interesting background. The history goes all the way back to Zipf's, and then to Pareto and Yuli, who basically discovered that for many phenomena, whether it's the size of the city or the frequency of appearance of words in languages, many distributions, the kth most popular by histogram telling item often shows up with a frequency that is 1 over k. Now clearly that is our scale-free phenomenon. It doesn't matter what k is, the chance of it shows up is 1 over k. So there's no specific characteristic scale, just like Pareto distribution. As you can see, Pareto here in the history of this evolution. And then back in the 1950s, there was this debate to say, all these are observations. The question is, how do you explain the observation? And there was a debate between Mandelbrot and Simon. And that debate is very similar to the debate about 10 years ago in early 2000 between preferential attachment and constraint optimization, except the context, of course, in 1950s was not the internet router topology. And very briefly speaking, before going to advanced material, preferential attachment says that when new nodes are added to a graph, they are more likely to be connected to those with a lot of connections already. So the rich gets richer, more connected gets even more connected. Conceptually, it says that the self-organizing growth mechanism of a graph leads to power law distribution. And mathematically, it says, turns out that sampling by density leads to a difference equation. We'll see the advanced material whose solution gives you equilibrium that satisfies a power law. In contrast, constraint optimization generates power law distribution in a very different way. It says that the graph topology is really designed with some objective functions and some constraints in mind, and yet the resulting topology can also show power law. Conceptually, it says that power law is the natural outcome of constraint optimization, with objective driven by economics, for example, and constraints driven by technology. Mathematically, it says that either entropy maximization or what's called isoelastic utility maximization under linear constraints. We're going to see these in the advanced material part of the video for this lecture. Either of them, among many others, would give rise to a power law. So there lies the main differences between preferential attachment and constraint optimization. So the question is, which one to use? Well, it depends on which one gives you the predictive power that you need on other properties, not the power law distribution anymore, because they both generate that. Other properties of the graph, such as robustness to a target attack of highly connected nodes. Will that break the network? Will that break just the edge? Whichever generated model can also have a predictive power on other properties that you care about should be the one that you use. And there lies an interesting story on the pitfall of generative models. In 2000, there was so much talk about the internet having an Achilles heel. It turns out that if you look at empirical data, you go talk to AT&T or Cisco Juniper, you realize that that's just not supported by factual data. It highlights the importance of falsification of any self-consistent theory through empirical data of the field that you're talking about. It also highlights the risk of overgeneralizing something called a network size, which is a fuzzy and mostly meaningless term, unless you provide some concrete meaning to it. By overgeneralizing it to some universally true property, it actually loses domain-specific functionality models, and thereby often loses predictive power and even lead to confusing, misleading conclusions, such as the non-existence of these Achilles heels. So we have seen generative models, reverse engineering of network topology, small worlds, and scale-free And later we'll also look at reverse engineering of network protocols. We have also seen the interplay between topology, say a graph and the corresponding matrices, versus functionalities, whether that's navigation or search, routing, or robustness to a specific kind of attacks. And the interplay between these two dimensions of what we call a network, whether social, economic, or tech network, will continue to show up in the rest of the course. As we conclude this point, the midpoint of this 20 questions about our network life.